Hi all, I am K. Surya, working as Assistant Professor in the Department of ECE at SNS College of Technology. In this video, let us see an application of smart sensors and devices, which is nothing but the LiDAR technology. So LiDAR stands for light detection and ranging. So in this video, let us see about the introduction of LiDAR, need and working principle, different types of LiDARs available, applications and its advantages and limitations. LiDAR stands for light detection and ranging, which is a remote sensing technology that uses laser light to create a 3D representation of the Earth's surface and objects. It is similar to radar, which uses radio waves and sonar, also sound waves. But LiDAR uses light specific pulse to laser light to measure the distances to a target. These measurements, combined with position and orientation data, are used to generate highly accurate and detailed 3D models, often referred to as point clouds. So, the need for LiDAR development is driven by its growing applications in autonomous systems, detailed mapping, environmental monitoring, and quality control across various industries. Advancements are needed to improve the accuracy, affordability, and processing capabilities of LiDAR to meet the demands of self-driving cars, robotics, precision agriculture, and smart city infrastructure. Further development also focuses on sensor fusion with other technologies, LiDAR, to create more robust and comprehensive sensing solutions. Next, let us see about the working principle. So, the basic principle of LiDAR involves emitting the laser pulses and measuring the time it takes for the light to travel to an object and return to the sensor. So, this time of flight measurement along with the speed of light is used to calculate the distance to the object. So the key components and its processes are first one is the laser scanner, which emits rapid pulses of laser light. So the wavelength of the laser light can vary depending on the application, but common wavelengths include infrared, green, and ultraviolet uh, wavelengths. Next important component is the scanner and optics, where it directs the laser beam and collects the reflected light. The scanner can be mechanical using rotating mirrors or solid state using electronic beam steering. Next important component is the photodetector, where it detects the returning light pulses and measures their intensity. The timing circuit precisely measures the time difference between the emission and reception of the laser pulse. Position and orientation system determines the precision, location, and orientation of the LiDAR sensor. So, this is typically achieved using a combination of global positioning system and the inertial measurement unit, which is known as IMU. Finally, the raw data collected by the LiDAR system is processed to generate a 3D point cloud. This involves correcting the errors, filtering the noise, and georeferencing the data. So, this is the process of LiDAR technology. So next one is the different types of LiDAR systems, which are broadly classified on several factors including platform, scanning mechanism, and wavelength. So basic three types are airborne LiDAR, terrestrial LiDAR, and solid state LiDAR. So the airborne LiDAR is mounted on aircraft such as airplanes and helicopters to survey large areas quickly. So two types are topographic LiDAR and bathymetric LiDAR.
So topographic LiDAR uses near infrared lasers to map the terrain, and bathymetric LiDAR uses green lasers to penetrate the water and map the underwater features. Next one is the terrestrial LiDAR, which is deployed on the ground, either on a tripod or a mobile platform, to capture the detailed 3D data of smaller areas. So here it is divided into two types, which is static terrestrial LiDAR and mobile terrestrial LiDAR. Stationary scanners used for high resolution mapping of buildings, infrastructure, and archaeological sites are used in static terrestrial LiDAR. Mounted on vehicles to collect the data while driving, often used for mapping roads, urban environments, and forest in mobile terrestrial radar. And the last type is the solid state LiDAR, where it uses the electronic beam steering instead of mechanical components, making them more compact, robust, and cost effective. So these are increasingly used in autonomous vehicles and robotics. Next are the applications of LiDAR, where it is used in a wide range of applications like agriculture, forestry, surveying and mapping, construction, autonomous vehicles, geology, city planning, and is used to monitor coastal erosion, map wetlands, and assess the impact of climate change. And it is also used for mine surveying, stockpile volume estimation, and safety monitoring. Let us see the advantages of LiDAR, where it has high accuracy, which provides highly accurate 3D data. It captures detailed information about the scanned environment. It can collect data quickly and efficiently, and it can operate in both day and night conditions. Also, it allows for data collection from a distance, reducing the need for on-site surveys. Some of the limitations are it can be expensive, especially high-end airborne and spaceborne systems, and processing of the data is computationally intensive and time-consuming. Also, objects can block the laser beam, creating shadows in the data, and the LiDAR data can be very large, requiring large storage and processing capacities. So these are the references for LiDAR. So let us take up the assessment question. So LiDAR works on the principle of the answer is emission and detection of light pulses. In a LiDAR system, the time of flight principle is used to measure the object distance. Thank you for watching this video.